Hello everyone, this video contains the second half of our derivatives and integrals short course video presentation. In the first half of the presentation, we have seen the derivatives and the differentiation process, and in the second half we will be revisiting the integral calculus. As I said earlier, for the derivative session, these topics are very broad, so we will be covering only a small portion of these topics. Otherwise, we would need much more videos about every single subtopic of these integral and derivative topics. We will start this session with the concept of antiderivatives. Antiderivatives also translates as indefinite integrals, but the difference between definite and indefinite integrals will come later. An antiderivative of a function f of x is a new function, capital F of x, such that the capital F of x dx equals to f of x. So let me translate it using everyday words. Derivative of capital F of x with respect to x equals to f of x. So the relation between capital F of x and f of x is the inverse of the derivative operation. And this is the main idea behind the integrals. And let's see indefinite and definite integrals and what do we mean by using one of these terms. An indefinite integral has no boundaries. You see a squeezed and stretched S symbol for the integral operation, and you do not see any numbers under or above the symbol. So it's just this S symbol, and this S stands for summation. So the integral sign is followed by the function f of x times dx. This form is called the indefinite integral, and after calculating the integral, the antiderivative of the given function, we do not apply any borders for the values of x. However, with the definite integral, you see there are boundary values, which are values of the variable x, under and above the integral symbol. This means that this integral is lower bounded by the given x1 and upper bounded by x2. So after calculating the integral, the antiderivative, we have to consider the boundaries and only find the values of this integral between these boundaries. Definite integrals are particularly useful when calculating an area under a curve or a portion of a given curve. So here in this figure you see a function, or maybe a portion of a function drawn as a partial curve. Here, in order to calculate the area under this curve, we should know the boundaries, so from which point until which point we will calculate. Otherwise, if this function goes to infinity, by its definition, we don't know, it's not given yet, but if it goes to infinity, then the area under that curve would also go to infinity. So uh, mm, depending on the situation, it may not be possible to calculate the area exactly if the boundaries are not known. So this is where definite integrals become useful. If we have the boundaries, then it will be easy to calculate the size of the area. Otherwise, in some circumstances, using limit formulas may be helpful, but we cannot always rely on that relation. Anyway, uh, if we draw little rectangles under this curve, and many of them, we can cover the area under the curve approximately. So there will be little gaps, and there will be some little area that flows over the curve, but the approximate area of this set of rectangles would be equal to or somewhat close to the real area of the area under the curve. And this is the main idea behind the integrals and the area calculation using the integrals. So if we make these rectangles bigger, then the error rate would be higher. The gaps that we cannot cover under the curve will be higher, and the result will be far from being a realistic estimation. However, if you make these rectangles very small, by small I mean very thin, then we will have too many rectangles in the same area between point A and B as the boundaries. We will have too many thin rectangles, but if we add the areas of these rectangles together, we will have something very close to the real area under the curve. So the approximate area under the curve would be the combination of all these rectangles together. And it can be represented with a summation formula with the well-known sigma symbol. And the area of one single rectangle would be delta x times the height of this rectangle, which is y something. So it should be a value on the y-axis. Let's call it y1 for the first one. So the area of the rectangle should be y1 times delta x, and we assume that delta x is the width of these rectangles, and it is the same. It's identical for all of these rectangles. So their height changes, but their width is fixed and all the same. So we can find the area of one rectangle by multiplying width and height, which is y times delta x. And k here in this formula, k here is the number of rectangles. So we have to make this addition k times to get the exact estimation. So the formula becomes k times summation of yk times delta x. And the exact area as definite integral would be integral from a to b y dx equals the limit of this summation yk times delta x, where delta x approaches to dx. This limit would give the exact area rather than a more basic estimation. Let's see a definite integral with a variable upper limit, which is also possible. The boundaries of the integral could start from a constant value, and could end with x, which is a variable, and the integral could be y dx. More proper form with a dummy variable could be integral from a to x y y of u times du, because y is also a function of x. So using a dummy variable makes things easy and look nicer. Let's see the area under a straight line segment. In the previous half of this course, we have dealt with straight line segments and continuous and discrete functions. Now we will see similar stuff here. But this time we are not working with slopes. This time we are working with the areas. So slopes are related to derivatives and areas are related to integrals. Here in the graph, we have a function y equals to f of x, but we can calculate the area under each straight line segment separately by using a definite integral with relevant boundaries. For instance, integral from x1 to x2 y dx could be the area under the line segment called L, the middle segment. Because in the x-axis, this segment is bounded with x1 and x2. And this is equal to 1 over 2 times y2 plus y1 times x2 minus x2. And this derivation is purely geometric. Let's see another example. The question asks us to determine the integral of y dx from 0 to 12 with the given function. Y equals to f of x is given in the chart, and it's a quite strange graph containing various line segments. And our boundaries are 0 to 12 for values of x. So we have to make the boundary arrangement on the x-axis because our variable is already x. We already said that integrals are all about the areas behind the function graphs like curves or straight lines. So what we should do here is to calculate the area behind the under the lines. So for the first line segment from 0 to 2, the area of that rectangle would be 2 times 20, which is 40. And in the second part, we have a straight line. There is no area under this line or between this line and x-axis, so it's 0. And then we have a triangle. Area of this triangle can be calculated using its specific formula, and it's 20, but it's on the negative side, so we have to extract this area from the original sum. Then the other triangle is very similar. Its area is the same, but it's on the positive side. So we add plus 20. We have another line here between 8 and 9. It's also 0. There is no area. And then we have a rectangle finally, and its area is 10 times 3, but it's on the negative side. So if we add all these area values, considering their positiveness or negativeness, we will get the result as 10. We have, in this example, we have exactly the same function, and the question again asks to determine the integral, but this time our boundaries are different. In the previous example, our boundaries was from 0 to 12, but this time it's from 0 to x, so we have a variable boundary on the upper bound. Before proceeding with the solution, we should look at the guidelines. First of all, if y is a non-zero constant, the integral is either increasing or decreasing linearly. And if a line segment is triangular, the integral is increasing or decreasing as a parabola. So it's not increasing linearly. Because if you think that integral is the antiderivative, then you will understand that the derivative of a parabola would be a straight line. So this is the inverse relation. Next, if y equals to 0, then the integral remains at previous level. This means that there is no change. Fourth, integral moves up or down from the previous level. So there is no sudden jumps, so it cannot change dramatically without a continuation. And lastly, beginning and the end points are good reference levels for the entire integral. Now we should revisit the question again. Integral of y dx from 0 to x equals to integral f of x dx from 0 to x. So by applying the guidelines, we get this graph on the bottom part of the page. By the way, how these values are calculated is not a mystery. If you do not get it, please do not worry, we will come to that very soon. Just like derivatives, there are a few representations for integrals as well. For instance, capital F of x equals to integral f of x dx. So this is one way of writing the integral of a function. Otherwise, I is also used. I stands for integral. I equals to integral f of x dx, where x is bounded by a and b. This is a definite integral because we have boundaries. In another form, I equals to capital F of x, where boundaries are between a and b. In this case, the result should be capital F of b minus capital F of a. So we are doing this because think about the area analogy. So we have an area which has strict boundaries on the x-axis. So if we subtract these two values calculated by the integral, then we can get the area in between these boundaries. Let's take a look at the common integrals. We have a table just like the one in the derivatives part. F of x is the subject function, and capital F of x is the integral of f of x times dx. Multiplying with a constant a does not change the result, just like in the derivatives. So a times f of x is a times capital F of x, where capital F is the integral of f of x. Addition is also trivial. addition of functions, what I mean. U of x plus v of x would yield integral of u of x dx plus integral of v of x dx, where u and v are functions of x, of course. And here there is a tricky one. Unlike the derivatives, integral of a constant number is not zero or is not itself. So integral of a constant number a is ax, a times x. So this is quite different than the derivatives, so please pay attention to this important detail. X to the power of n, where n is not minus 1, is, and the integral of this is x to the n plus 1 over n plus 1. An integral of e to the a times x, where e is a constant number and x is the variable, is only e to the a times x over a. So the main part of this function, as in the derivative counterpart, does not change, but we just divide the outcome with a. So working with the magical number e is quite fun. Integral of 1 over x is ln x, natural logarithm. Integral of sinus ax is minus 1 over a times cosinus ax, and integral of cosinus ax is 1 over a times sinus ax. And sinus square ax is 1 over 2x minus 1 over 4a times sinus 2ax. Okay, this is quite hard to memorize, but you can always derive it yourself. Cosinus square ax is similarly 1 over 2x plus 1 over 4a times sinus 2ax. And x times sinus ax is 1 over a squared times sinus ax minus x over a times cosinus ax. X cosinus ax is 1 over a squared times cosinus ax plus x over a times sinus ax. These are also complicated, so don't worry if you cannot memorize it, it's quite hard. Among the rest, ln x is quite important. Integral of ln x is x times ln x minus 1. And 1 over ax squared plus b becomes 1 over square root a times b times arctangent root of a over b with the degree x. We have a few subsequent examples here, and we will determine the following integral in each case. Z equals to integral y dx. The given function is y equals to 12 times e to the 4 times x. And z here becomes integral of 12 times e to the 4 times x dx, which is, if we use the table to calculate the integral of e, here we have it, e to the a times x is defined very simply, e to the a times x over a. So we have to replace it here. So the integral becomes 12 times e to the 4x over 4 plus c. And this c comes out of nowhere because we should think integral as the antiderivative, so inverse of the derivative. And since the derivative of a constant number is 0, there could be any constant number and we cannot have a clue about that. So this is a downside of having an integral. there can be a constant number, or they may not be a constant number. We don't know, but we have to put a symbolic number c to represent if there is any constant number here in the original form of this function. And eventually we get 3 times e to the 4x plus c. C may or may not exist. Another one here, y equals to 12 times x times sinus 2x. And 2 is inside sinus, please pay attention. So z becomes the integral of this. And it is, again, using the table. Let's look at sinus. Here, we should write this formula directly. And oops, just went too much. Yeah, here we have to write the formula for sinus 2x, and we will finally get 3 times sinus 2x minus 6x times cosinus 2x plus c again. In the next one, y equals to 6x squared plus 3 over x. Here for 3 over x part, we can use the table again. Here we have its ln x. And in the next step, we will get integral of 6 times x squared dx plus 3 over x dx. Since these are addition of two terms, we can take their integrals individually, and this will be much easier. Eventually we will get 6 times x cubed over 3 plus 3 times ln x plus c, and which makes 2 times x cubed plus 3 ln x plus c. By the way, I have to note that when we are working with definite integrals with constant boundaries, since we subtract to result calculated with one boundary, the lower boundary, from the result calculated with the upper boundary, the constant number, the possible constant number c as a product of this integral will be disappeared, because the first one, the integral calculated with the upper bound, will have a c value, and the result that is calculated with the lower bound will have another c value, but these c values will be the same. So when subtracting these two from each other, the c values will be neutralized. In the upcoming examples, we will determine the definite integral in each case as defined below. I equals to integral from a to b y dx. Now we will be working on definite integrals. Here I equals to integral from 0 to pi sinus x dx. So integral of sinus x, we already know that from the table, it's minus cosinus x. And our boundaries are from 0 to pi. So we can just write it here exactly as they are. And we should now calculate minus cosinus x using pi and using 0. So then we should subtract the lower bound from the upper bound 1. And the result becomes minus cosinus p minus cosinus 0, which will be minus 1 equals to 2. A very fun example. Second one here, I equals to integral from 0 to 1, 8 times x times e to the minus 2 times x dx. Looks quite complicated, but in fact not, because we have e, and e is the magical number. Working with e is very easy when we are taking integrals or derivatives. In the next step, Using the shortcut formula of integral of e, we will get 8 times 8 can be disregarded. It's a constant factor here. The result would be 8 times e to the minus 2x over 2 square times minus 2x minus 1 from 1 to 0. And now we should calculate this function 2 times, first using 1 and then using 0 as the value of x. Then we will get 2 times e to the minus 2 times, inside the brackets, minus 2 times 1 minus 1, outside the brackets, minus 2 times e to the minus 0 times, inside the parentheses, 0 minus 1. And finally we will get minus 6 times e to the minus 2 plus 2, and e to the minus 2 can only be calculated using a calculator or an online tool, and if you make this calculation you will get something close to 1.188. When we were talking about the derivatives, we have seen displacement, velocity and acceleration and the relation between them. Now when we are working with integrals, we can revisit these topics and see the relation between these variables from a different angle using the integral approach. So a can be written as a function of t, which is time. So a equals to a of t, which is acceleration in meters per second square. Likewise, the speed, the velocity v, can also be written as a function of t because it changes in time, or at least it may change in time. V of t is velocity in meters per seconds, and y is the displacement in meters, and it's of course another function of time because it will, if there is a velocity, then y will definitely change in time, and we have already seen this and have proven this in the first half of this presentation. So y of t is displacement in meters, and we have already seen that dv dt, derivative of velocity with respect to time, gives us a of t, the acceleration per time. And dv here is dv dt times dt, which is a of t dt, just from an algebraic play. Algebraic play will give us this relation. And from this point we can take the integral of dv. And integral dv would be integral of a of t dt. So we can take the integral of both hands of this equation on the above line. And by logic we will get integral of dv as v. And we can make a substitution of v, and we will get v equal to integral a of t dt plus a constant number c1. Similarly, dy dt is the derivative of displacement with respect to time, and it is clearly the speed, which is v of time. And from here dy, we can leave dy alone on the left side of this equation, and dy would be equal to dy dt times dt, which is, as we show here, v of t dt. And now we can take the integral of both hands, and y would be equal to integral v of t dt. So let me summarize it with easier words. In the top equation in this page, we see that integral of acceleration gives the speed. And likewise, integral of speed gives the displacement. So this relation is the exact inverse of the relation with the derivative approach. So we get the same ties, but we analyze it from different angles. It's very impressive, I think. Furthermore, using definite integrals, we can provide an alternate formulation. So the velocity v of t can be written as a definite integral from 0 to t a of t dt plus v0, where v0 is the initial speed at time 0. So we do not know what time 0 exactly is in practice, and we do not know the initial speed at that time 0. So it could be anything, but if we should work on numbers, these values must be given beforehand as a prior knowledge. And similarly, displacement y of t is expressed as integral from 0 to t v of t, velocity, v of t dt plus y0. y0 is the initial displacement at time 0. We now have an example regarding that. An object experiences acceleration as given by a of t equals to 20 times e to the minus 2t. And v0 is given as 0, so initial speed is 0, and y0, initial displacement, is given as 0. And the question asks us to determine the velocity and displacement using this prior information. We can calculate the integral of a of t, because we already know that dv dt, which is the derivative of velocity with respect to time, is equal to a of t, and it is given as 20 times e to the minus 2t. Hence, v of t here is the integral of this term, and it will be 20 over minus 2 times e to the minus 2t plus c1, which is equal to minus 10 e to the 2t plus c1. And v0 here is already given, so we can set this equation to 0, and we can then solve this equation for c1 and find what is c1, because we already know that v of 0 equals to 0. So minus 10 e to the minus 0 plus c1 is minus 10 plus c1, because e to the minus 0 is just e to the 0, which is 1. So minus 10 plus c1 equals to 0. Then c1 is positive 10. Sorry, c1 is positive 10. And in this case, we already learned that what c1 is, and v of t becomes 10 minus 10 times e to the minus 2t. We already discovered what velocity is. Now it's time to find out the displacement y of t. And we saw here it is the integral of velocity. So we have to take another integral here. Integral of 10 minus 10 e to the minus 2t dt will give us the result. And it is 10 times t plus 5e to the minus 2t plus c2, And here with the same technique we can resolve what C2 is, because we know we already know y0 is equal to 0. So if you write 0 instead of t in the above equation, we will get 0 plus 5e to the minus 0 plus c2, which can be simplified as 5 plus c2 equals to 0, and then c2 will be minus 5. And eventually we will get y of t, the displacement, equals to 10t plus 5 times e to the minus t minus 5. We could also rework the previous example by using the definite integral forms. I will not read this solution out loud, but you can stop the video here and analyze the solution, or you can try to solve it by yourself. Finally, the example question asks us to plot these three functions of the preceding examples. A of t is equal to 20 times e to the minus 2t, and v of t equals to 10 minus 10 e to the minus 2t, and y of t is 10t plus 5e to the minus 2t minus 5. So you can easily plot these functions using MATLAB, or if you are good at Python, that's also possible, or you can use Wolfram Alpha or other tools like that. Here is the MATLAB code to draw all these three functions. You can try it yourself, and the result would be like that. The acceleration decreases with a dramatic rate, and since there is acceleration, we have an increasing velocity, but the rate of this increase in the velocity is dropping. It is decreasing. The velocity is increasing, but the rate of increase in the velocity is decreasing because the acceleration is decreasing. But anyway, displacement is increasing quite fast because we have a good amount of velocity. At first, from the point 0, the velocity is very small, so displacement is also very small, but since the acceleration is high, velocity will be good in a moment, and the displacement continues to increase with a good speed. So this is the interpretation of these velocity, displacement, and acceleration terms. We have already seen the derivative style relation between them and the integral style relation between them. And now finally we plot them on the graph and make comments about that. So I hope that this course provided a brief understanding of what derivative is and what integral is, and what is the relation between derivatives and integrals. So we are done for today. As I said earlier, calculus is a huge topic, and inside calculus, integrals and derivatives are huge subtopics. And if there is no time limit, then we could continue about these topics for hours and hours, and it won't be possible to cover all the details. So that should be fine for now. Thank you very much for listening.